All right, I've just got a little proof of concept here. What I'm doing is a 4-wire remote sense on this cell, and I'm just using these monster alligator clips. I was trying to come up with a better way to mount this because 110 amps continuously is going to be pretty tough on this, but they don't actually heat up that much. I used this thermal imager here, this Seek imager or whatever, and they don't get that hot. They're only getting to maybe 45 degrees C or whatever. I'm going to blow a fan across it for the long-term stuff. But anyway, we'll be able to just test all of the cells. This first cell here is the 75 amp. It's not the one we're testing now, but 75 amps of regen, and then it'll be 36.2 milliohms of assist, which will be about 110 amps when the cell is full, and then it'll be maybe 90 something amps as the cell gets down to like 3.3 volts. So anyway, I've got that hooked up here. I'm going to be using 2 Lambda gens. This one is the only one I have that supports USB. I have them that do GPIB, but the USB is just easier to use, and so you can daisy chain them, so you just plug a cable in the back and then you can connect them, and you can talk up I think like 16 of them if you want. But anyway, this one is going to be controlling both itself and this big boy here. And I'm just going to write a LabVIEW program. I'm installing an older operating system on this old Mac Mini so that I can run. I have a version of LabVIEW from 2010 that I like to use. Even though LabVIEW is free now, if you do the community edition stuff, I just prefer the 2010 version. It's quicker, easier to use for me. It's probably not actually faster, but it's easier to use. So here I have my, this is a 600 amp N-channel MOSFET. Its RDS on is 700 microohms, so it's only about 2.5 feet of this 4-gauge wire in its RDS on. And I didn't have a heatsink that it would easily mount to, and so I had this part that I designed for another product, and I'm just using that as a big thermal mass to sink power into. And so the way this is going to work is, I need to disconnect this supply here. So I'm unplugging these. Obviously I need to put it all together. I'm just kind of testing everything out here. So we're going to hook, our source is negative here, and then we'll hook up our drain here on the high side. And so the way this guy works is we can set our output current here, it's 110 amps, and then this guy is actually going to control whether or not it's on or off. So when I power the gate, which is what this is doing, we're sinking our current into there. And the 0.49 volts here you're reading is incorrect because we don't actually have our remote sense leads hooked up. But if you look at it with a multimeter, I did the math earlier, I think it was like 70 millivolts, so it's very, very low. Now as far as characterizing the actual cells, I'm getting at like 20 amps of charge, I'm getting about a milliohm, and then even at 125 amps of charge, so regen, it's only 1.12 milliohms. So certainly this is not the cell that was referenced, the other cell here, because the ESR would be much higher. We're only rising 120 microohms with 125 amps versus 20 amps. So this cell can certainly handle probably a couple hundred or even several hundred amps. Now I'm not pushing this cell too hard because you might notice I'm inside right now. I'm going to wait to really abuse the cells until I get outside, just in case this is outside of spec, which I'm sure it's not. But anyway, yeah, this is kind of all coming together. And so the next video will be it probably actually running once I just need to whip together a quick LabVIEW program. And of course, the reason I'm doing all of this right now is one, to procrastinate so I don't have to work on firmware, but two is this test is going to take several months to get useful data from for every cell that we test, unless we just thrash a cell. So like, for example, if this cell only lasts 100 cycles when we're doing this really extreme case, this first test here that I've written on the side is the most extreme that it would be in an LIBCM car, at least for now, when we have the plus 40% current hack. If we can get the current higher later, obviously, then it might abuse the cells more. But anyway, so if this lasts 600 cycles and we can do 21 tests per day, so we'll just say it's 600 cycles divided by 21. I don't do math in my head, so it would actually take a month almost to get that data. So anyway, I want to get this started now so that we have at least some data. You know, this will be worst case, and then we could do a more realistic test. Of course, we need to do it across temperature. There's a lot of testing to do. We have 12 cells to test, or probably 11 or 10, just depending on how damaged they are. I did look at the bottom of this module here that has the scratches on it, and what I did is I put some tape over where these scratches are, and then I think that this tape might have already been there, but I definitely put tape here and there. So we'll be testing the cells that are not mechanically damaged first, and then when I look at these later, I think I might have to destructively tear this apart to see how thick this sidewall thickness is. So it'll be months from now probably that we look at that. So anyway, that is the state of the test now. My install just finished, so I'm gonna go ahead and fire up some LabVIEW and write a quick program to just charge, discharge, and log the data. So as always, thank you for watching.